Okay, anybody? Yes.
So how do we differentiate between carry flag and overflow flag? Because like sort of doing the same.
I'm sorry. Can you just repeat that thing?
The difference between carry flag and overflow flag.
Okay. So if it is like, I need to brush up my things about digital logic. But, if I remember, the overflow would occur when, your result, uh, if, if you're adding two numbers and, if something goes to carry, then, it is the carry is like, something that, it is additional thing. But, if you're adding numbers, which is much larger than that, and lot of uh, digits are falling off, then, it is overflow. I'm not very sure about this answer. I think I will have to check this because, this is a digital logic thing. I should know this, but then, it is too basic. So not a excuse to forget, but, I have forgotten. But, you can also check this, I mean, the answer should be easily available.
Okay, I'll see it.
I'm sorry?
I will see it.
Okay, okay. Okay, something else I would like to tell you is, we open the Okay, can you see the slide?
Yes, sir.
Okay. So I would like to say some things. First of all, the relations which you need to know is that, frequency is equal to 1 over time. So I can ask you the question in terms of frequency, and then, the data is in terms of frequency, and answer I might ask would be in terms of time. So you have to read the data very carefully and give the answer. Failure to read the data and, giving an answer in terms of frequency, saying that, I forgot to see, is not right, because even if you do a job, if you don't pay attention to the work which you have to do, and, you give the answer of something else, then, you will not you'll be held responsible for that. So please remember this. If I ask the answer in terms of time, then you are supposed to answer it in terms of time and not in terms of frequency, and vice versa. So that is first thing, which you need to know. Second thing, in pipelines, I can ask you the question about, some particular pipeline, being divided into, say, I am converting 5-stage pipeline into 7-stage pipeline, or 11-stage pipeline, or whatever number. Then you have to carefully see which pipelines are broken. So suppose I have done fetch stage into, say, fetch 1 and fetch 2. Then, the real fetching will done at end of this F2 and not between F1 and F2, because this would be more or less a junk data. And, this dividing up of a particular stage is done to speed it up, especially in fetch stage. you know that, there is a branch predictor which you have to look for. And, once the branch prediction comes, then, you have to decide whether to fetch according to what the PC value, or, you have to take it according to the target value which you are saving. And then, you have to actually go and fetch it. And, you know that there are problems in fetching. So fetch stage is usually divided into two parts. I can also divide it up into three parts. So faster I want to make my processor, more pipeline stages would be required, because any pipeline stage which is taking more time, you have to divide it into number of stages. Does anyone have any? Let's go topic wise. Let's see if you have any question in terms of pipelining. Okay, so you don't have any questions or doubts in? Yes.
Sir, if we are given that if we are supposed to consider 5-stage pipeline, then
Okay.
we by ourselves consider that right read write stage and fetch stage are in half of the cycle, means read write is in
Yes. Yes.
first half and fetch is in second half.
Right. So normally I would say that, suppose if I say consider a 5-stage pipeline, and it is fully forwarded, I mean, it is full data forwarding is there, then you're supposed to assume that, I mean, whatever the tricks which we have discussed till now is there. Even if I don't give it, you are still allowed to assume that, full forwarding is there. But if I say that, there is no forwarding, or forwarding only between certain stage to certain stage, then, that is valid. So if no mention is given, if I just say consider a 5-stage pipeline, and then I go forward describing the problem, then, you assume that there is full data forwarding, and, writing into register in the first half and reading in the second half.
Okay, sir. Thank you.
Any more questions in this? Okay. So third topic we want to go by is memory, or memory hierarchy to be precise. Does anyone have any question in memory hierarchy? So just to remind you or refresh your memory, that in memory hierarchy, we first check with the direct map cache. Then I told you what is the difference between index, tag, and block offset. So suppose if I ask you or give you example of, say, two systems, two memory systems, and each memory system has certain values, like you figured out in the problems which we are given, that what is the block size, what is the access time, and all that. Then I ask, this is system A with certain configuration of memory, and this is system B. Now, which one is better? So then, you have to figure out that, at certain point, you have to find out the value for system A, find out the value for AMAT for system B, and then compare it and say, okay, system A is better than system B. Or I may ask a question that, for what L1 miss rate B might be better than A, then, you have to find out that particular thing and get the answer. In AMAT, we have shown that is average memory access time. So you should know that fetch and the memory access cycle, basically this should be for data, but we write data memory or whatever. So this is fetch is for instruction, this is for data. So these two stages in a 5-stage pipeline are the ones which can cause a disaster in your performance of your pipeline. I mean, they may go like, totally throw the thing off if they are not properly designed. So that means if you get lots and lots of L1 cache misses either in F or in D stage, then that means the performance of your processor will go down. Okay, so you have to remember that whenever we talk about average memory access time, we are talking about this stage and this stage. Does anyone have any question?
Sir,
Yes.
sir, in the AMAT problem which you solved during the lecture, in the first question's answer, the question was like, what fraction of all data memory references cause a main memory access? So, sir, in that answer, you have not considered the L2 means there is a mention that 50% are dirty. So in the L2 hit case also the 50% would go to the main memory. So the answer is just changing by 0.02%, but we should consider that, right?
Okay. I don't remember it often. Let me just open it up and see. Okay, so the question here asked was that what fraction of all data memory references causes a main memory access? Okay, so main memory access, so I mean the data references which are coming through from the processor, and how many those references have to go to main memory. The traffic of the dirty blocks is between L2 and main memory. It is not coming from processor, and that is also all internal parts. So the question which was asked was that, computer, let's say your processor is throwing 100 data memory references. So out of those 100, how many will end up in the main memory? So that was a simple question. So in that case, what was not asked was that processor doesn't care what is internally happening between L2 and main memory and what is the bookkeeping thing. Those things would come into when you do AMAT. So what you see in the first question is we are not calculating time or anything. We are just saying that, if the processor throws 100 requests at L1 data cache, how many requests would end up in main memory? That was the only question.
Okay, sir.
Right. So you have to consider the traffic between L2 and main memory when there is a problem of dirty blocks being replaced. That will be part of the time. Right. There is the average memory access time, and that would increase the time. But for the first question, I have not asked anything about time. It is just a simple thing that, how many data memory references, which is like, posed by the processor, is going all the way down to main memory.
Okay, sir.
Okay. Any other question? Okay, so then we move forward to the fourth topic, which is branch prediction. So in branch prediction, we talked about, mainly we concentrated on 1-bit predictor, 2-bit predictor. So this is mainly the prediction bit, which actually do the prediction. So in 1-bit predictor, you have just, it's like a coin toss. So whether this could be 1 or it could be 0, right? So based on this, you're predicting. 1 means, suppose if you have taken 1 means take the branch, and 0 means don't take the branch. Then, this is a 1-bit thing. And 2-bit thing, you have got 4 states, and 2 of which means take the branch, and 2 of which means don't take the branch. So then, based on, values, so let's say 0, 0 and 0, 1 means don't take the branch. And this means take the branch, which is 1, 1 and 1, 0. So then, based on this, your branch will make a judgment. You should also remember that I can change the state table. So I can give you an example where 1, 1 would means strongly not taken. Okay, so because, since I'm the designer, I can design anything. And, I want to keep it this as strongly not taken. Also, I can give you an example where I can say that, my predictor bit or, prediction starts from bit 1, 0. Right, so when it starts from 1, 0, then, it is something like this. Normally, we say that, we start from 0, 0, but I say, no, I have designed my thing in such a way that it starts from 1, 0, which means taken. Right. So then, you have to take that as the data and, move from that point onwards that, what would happen for different cases. Then, we talked about pattern, branch pattern, because we saw that 1-bit and 2-bit are not very good in, say, 1-bit and 2-bit are all very good for loop kind of keys and or lots of ends followed by a change of pattern at some point. But it is not good at like, something which is going like this. Then, this would totally bomb and this would also give partially correct results. So to get prediction which is correct for this kind of branch, you have to have a pattern. So then, you can have 2-bit pattern or 3-bit pattern or 4-bit pattern or n-bit pattern. So based on the pattern, you set or reset your prediction bit. If it is 1-bit, then, you can say if this is the pattern, then my prediction is taken. If this is the pattern, my prediction is not taken. So that is the thing. So do not confuse between the prediction bit and the branch history bits. So branch history bits are 4 here, but prediction bit is generally 1, or I can ask you a 2-bit predictor. So that is the difference between the two. Also, I can throw some unusual things like, one thing which I gave you in the homework problem, which you solved in the lab, that, because of the space constraint, each one had its own pattern, each branch. But, the pattern was like taken on. What I gave you was that, there are 4 patterns. I guess the problem was of 2-bit pattern history. So this is common to all, to the whole branch history table. And, there were 2 branches which were using, I believe they were using TT. And they were causing problem because, both of them thought that, this is my thing. So you have to be careful. I mean, you may say that this is not the most optimum solution, and each branch should have this much hardware with it. But then, any additional electronics means you are paying for the cost. And if you want to have a cheaper thing, then, you can say, okay, I'm ready to accept that, there might be a wrong branch prediction, but, I don't want to invest too much money or power in implementing this. So that is what we studied in branch prediction part. Do you have any question in that one?
So I have one doubt.
Yes.
So in this initialization step can be any of the 4 states.
Yes.
So that will be given in the question, or we should assume something?
If it is not given, then you have to assume it starts from 0, 0, because, that
Okay.
is a norm, right?
Can be not- Yeah, right. Yeah.
Sir, if 2 addresses are using same prediction, like then the thing TA thought was that one of the branch would not affect the prediction, and only one branch will decide the prediction. Is it the case?
Well, let me just rephrase. I mean, I don't know what exactly he said, but let us. So let us say there are 2 branches which has got the last 3 bits as 1, 1, 0, and 2 branches unfortunately have this 3 bits, right? So it's a 8 entry table. So it starts from 0, 0, 0 to 1, 1, 1. Now, if 2 branches are resolving, both of them would think that this is my predictor bit. So when so suppose, I mean, I guess the one example was always taken, right? And the first branch was something like this: taken, not taken, taken, not taken. So this would be, as you can assume, will be 50% of the time correct, because the ones. See, this one, say the branch is taken, so it would put its next time, when it comes, I should take it. It will be correct for the second branch. Now, when it comes to here, it says, no, it is wrong. My prediction was taken, but actual outcome is not taken. So next time when this particular branch comes, I would say not taken. But, then, this branch would also think that this is it. So, I mean, it would say, okay, it is not taken. So I will assume that branch will not be taken, but in reality, it will be taken. So it will shift it to taken. And then here it will be turned out to be correct. So you can assume that both of them are affecting each other. And this is turning out, so it is turning out to be 50% correct. Now you'll see, I mean, if you probably your TA was trying to say this, that, if I have 1-bit predictor and I have a pattern like this, then, I mean, I will get 0% accuracy, correct? And if with the pattern like this, I will get 100% accuracy if there was no conflict of aliasing. When there is aliasing, this one is taking a hit by 50%. It is coming down. So instead of 100% accuracy, it is giving me 50% accuracy. But this, actually, its performance is improving, which is a unintentional side effect. that, from 0% accuracy, it is going down to 50% accuracy. I mean, it is not a desirable thing, but, it just happens. So probably he must be mentioning that, or he or she must be mentioning that.
Sir, like if he started from this TTT branch, like first is taken, then the second branch will also see taken. But when it
Right.
comes back, then again,
Right.
like
I lost you for 2-3 seconds. Can you repeat your question?
sir, 1 minute, I'm just not getting the exact thing. He said that one branch will be 100%, other will be 50%. He was saying something like that, as long as I remember. I will just ask some
No,
of my classmates and tell.
this is the correct interpretation. See, the first branch, if I am not mistaken, was resolving as Tn, 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 right? Taken, not taken, because of the data pattern. And the last branch, which was like, if R1 is less than 75,000, then take it, or some such thing. So it was always taken. Now, unfortunately, there was aliasing between the outcome of this branch and this branch. If there were no aliasing, then this one, as you agree, would give 0% accuracy, because first time it is taken, second time it is not taken. So, your predictor would keep on flipping, and every time it would predict wrong based on the previous result. And this one, your 1-bit predictor should be very comfortable. It will give you 100% result, because, the pattern is repeating. When aliasing occurs, then, you have to see what happens. So here the prediction, this one branch would say it is taken. It is okay for this one. Since this one is taken, then it would say, okay, next time when this branch comes, I will ask it to take the branch. But it is not this branch which is coming. Then it is this branch. But, unfortunately, both of them fall on the same thing. They think that this predictor bit is theirs. So when it sees taken, I mean, it will say, okay, next branch also has to be taken, but actually it turns out to be not taken. So that's why it's 50%. So this is the correct version.
Okay, sir.
Do you understand this, or you have doubt in this?
Yes, I got this one.
Okay. Any other question? Okay. So after this, we went to superscalar processor. We did talk about memory a bit. There's the NOR, NAND, flash, and other things, which is good and you need to know. Also, when I say that, a processor has got 4 GB of addressable space for a 32-bit processor, so it means that, this 4 GB space, or 4G or 4G addresses are there. So now this one would be divided into several different types of memory. Like, in your phone, you have got random access memory, you have got flash, you have got NAND flash, you have got NOR flash, you have got some other type of memory. So all of them would be divided in a address space which is of this 4G part. So that's why, again, you need to know that why memory map is important, because this is, some of it might be only read-only memory, right? This might be a boot sector, and it is between some address to some address, and this is in a particular type of processor made by company A. But board made by company B, or computer made by company B, has not provided ROM between this address and this address. It is something else. And then, if you try to run your program, it will keep on getting the interrupts that, okay, this is undefined data access or undefined instruction access, that, there is nothing over here, and you are asking me to write something into read-only memory. So the 4 GB space is shared by all different types of memory, and because some types of memory are read-only memory, or some types of memory are reserved memory like boot sector, and you don't want anyone to write on it, or some type of memories are reserved for system and not allowed by user to write in it, or even read in it, because they may have partition to make a secure system. They may have partition that user cannot access certain memory and can access certain part of memory. So those are the things which you need to remember in memory hierarchy. The sixth topic was superscalar processor. Or does anyone have any question in this one?
Sir, can you please repeat what do you mean by a memory map?
Okay. So memory map is like, if you read the spec sheet given by manufacturer, they may say between memory address X and X dash, I'm giving read-only memory. Between Y and Y dash, and there might be gaps in the middle. Total address, should start from 0000, 32 zeros, and end at 32 ones. Okay. So between this, then I say this is of my flash memory. This is my boot memory. So this, someone has to tell me that, where everything is and where my program would be. So if I write a program and say, store some part of the memory into a particular address, I need to know between which address to which address I'm allowed to store my memory. Right? Because other memory, like, if this is a boot sector, I'm not allowed to write anything into it. And if I try to, so, and this might be like vacant, right? There might be nothing in these addresses. So like, if I say there's possible 0 to 999 boxes you can have, but I'm allowing you, say, between 0 to 10, I have certain type of boxes. Between 40 to 60, I have certain type of boxes, and between 90 to 100 or 90 to 99, I have third kind of boxes. So if I say I want to put something into box number 11, and then they will say there's nothing like box number 11. There is nothing like box number 21. There is nothing like box number 39. So just like this, the addresses are also like that, and this is your memory map. Does it make sense to you?
Yes, sir. Yes, sir.
Okay.
And sir, are all memories in the address in same address space?
Well, address space, theoretically, the address space for a 32-bit processor is like 4 GB, right? So it can be between all zeros, 32 zeros to 32 ones. So I can't go below 0000 or above 1111. So if I want to put my NAND flash somewhere, it has to be between those two numbers, between the floor and the ceiling.
Yes, sir. Yes, sir.
I'm not sure whether I understood your question.
Yes, sir. Sir, is the hard disk also addressed by this?
Okay. So hard disk is virtual memory. So you will see that, they like to call something as paging. Now, page and block, they are the same thing, right? But, the operating system people and hardware people, they speak different language. So they talk about paging. Now, your hard drive is like 1 TB. Okay.
Yes,
Now,
sir.
this thing has no way to know this. It cannot address 1 TB thing. So initially when you write your program, it is written using virtual address. So virtual address might be 40 bytes or whatever. Then, your RAM is working on physical address, but that means the real thing. So your RAM, so whatever memory hierarchy we studied, your RAM cannot be bigger than 4 MB. If I assume that other types of memories are not there, flash and other things are not there, then your RAM can't be more than 4 GB. So if I want to translate this address into main memory, so just like we had to do a mapping of main memory into cache, similarly you have to do mapping between virtual memory to physical memory. Right, so your virtual memory, that is your hard drive, may have 40 bits of address, and let's just say that your laptop is only has 32-bit processor. So physical memory addresses are only 4 GB. You have got 1 TB. So the address from here to here, you will have to do mapping, just like you have to do mapping of addresses going from main memory to cache. Does it make sense to you?
Yes, sir. Yes, sir. I got it.
So, I mean, the paging part, you will study in operating system part. And, at that time, you remember that, page is the same thing as block.
Yes.
Okay. Any other question? In Superscalar, do you guys have any questions? Okay, so let's go to the final topic of do you have any question in multi-core processor? Okay, so I think I have told you this many times, but we went from 3 stages. First was inline processor. Now you know why the simplest process is called inline, because in superscalar there is multiple parallel lines, whereas inline processor it is just like a train. So this has got certain issues. We talked about data hazard, structural hazard, and control hazard. All of them are carried forward to the second topic, which we studied as superscalar. And superscalar, along with all the problems of here, has this idea about issue stage. That is a new part where you are doing out of order execution. And when you are doing out of order execution, you are supposed to check that there is no raw hazard between them. Otherwise, it would be a disastrous thing. And so that you have to check for raw hazard, and then you have to have reservation stations so that raw hazard can be taken care of, as we saw in Tomasulo algorithm. And then if you put more than one superscalar processor core together in one thing, you come down to multi-core, which is now there in your laptop or mobile phone. So it has, along with this problems and problems of superscalar, it has got its own problem of cache coherence. So how to update the value of all the caches together. Now there are many algorithms which are out there. Most of the algorithms, the companies won't tell you what algorithm they are using. So we studied one of the most simple and basic algorithm, which is MESI protocol. And MESI protocol teaches us to do something. MESI protocol is also known as one of the most conservative protocol. So they know you do things very methodically. Now, to some people, it may not be fast enough, or you may feel it is wasting time. So now the second protocol which has come is MoESI protocol. So there is additional state or flag called owned, or which O stands for owned. And that means you're allowing two processors to transfer data between themselves without updating the main memory. So, I mean, it has got its own issues. And then, they have come up with many other algorithms which are much more complicated. But, the final idea is this, that, how do you maintain cache coherence so that, no processor or no core is using stale data, or it is getting the most best updated data which is out there. The only way to avoid a lot of cache coherence issues and traffic on the interconnect bus is to avoid use of global variables. I mean, they are the ones which needs to be shared between different threads which are running on different cores. If you don't have any global variables, then each core would keep on doing its own job, and will give out the answer, and finally answers would be collected at some place, and you will get the result. And that mostly happens in your graphics processor. Any questions from multi-core processor? Okay, so I think we have done a quick walkthrough of all the topics that we have done. Now the questions which might be, which will be asked of you. I mean, I've not yet designed the paper, but in this one, I'm not going to ask all the questions as multiple choice or one-liner. This time, my TAs and I would be taking some pain, and you guys would have to solve the problems. That means you'll have to type the solution. In typing the solution, you must remember you will get marks only if things are properly explained step by step. So first of all, like say for AMAT, first of all you have to explain your logic. Then you have to put in the formula. Then you have to put numbers in the formula, and then you have to give the answer. If you say don't write the formula, or you may think in your mind it's too simple, I know what it is, and you just put the numbers and get the answers. Even if the answer is correct, you will not get the marks. So please remember this. Do not come back to me saying that my answer is correct, but why I have not gotten the marks? Because sometimes you get a correct answer by fluke, right? You may not have understood something, but it may turn out that even if you have done it the wrong way, the answer is correct. So I will not assume that you know the correct method unless you first explain the problem in words, then put the formula, then put the numbers, and then give me the answer. Okay? And that is true for all the problems. So most of the problems which you are going to do will not be multiple choice. You will actually have to type out the questions and answers. And there might be some ARM programming related question, but not more than 20%.
Hello, sir.
Yes.
Sir, is it true for all the questions, or will you mention that we have to We have to write the logic and everything, or do we have to do in every question?
You have to do that in every question. So, I mean, you will easily figure out multiple choice is multiple choice, right? So you just have to select one answer, and there, no explanation is necessary. And there you may have negative marking because you are not asked to explain your logic. So there, if someone is gambling, you want to catch them. So there would be negative marking. If a question is asked, like, your problem statement, which is given, and now you're aware of the problem statement, where choices are not given. You are just asked that, what would be the answer of this? So you are supposed to do all calculations you are supposed to type out the logic, then the formula, and then you have to put the answer. There would not be negative marking in the problems which are asked, in which you have to explain. If you have made some mistake, you will get 0 marks. But if we find out that you have copied something from someone, and it is very easy to catch, because a group of TAs would be checking all the questions. I mean, same questions in all the papers. So it is not that TA 1 is going to check paper number 1 to 30, and TA 2 is going to check 30 to 60. So a single TA or a group of TAs would check, say, question number 4. So then they will get a complete idea that, I'm getting this particular type of answer with particular language, very often. Then, they would flag those, and then, I will make a call that, if it is not possible for everyone to use same words and, same style of writing formula, and, you may end up being penalized. So there will be negative marking if you are caught copying. Otherwise, for wrong answers, by mistake you have made in the formula or mistake you have made in calculation, you will not be penalized. And for practice purpose, we have done enough problems. So problems would be something like that. It would not be exactly like that, of course. Otherwise, it would be like 12th standard exam. I will be throwing in some spanner. But, if you just follow the logic, I mean, there is nothing much that is different. So you just have to apply yourself, and, you figure out. I would like to put some questions which you have not seen before, though the method is same. That is just to check how smart you are. There might be some problems, which you may have done before, because, that is for average to below average students. And, if you want to get good marks, then, you have to be able to solve some problem which of the type you have not seen before. But, the logic and everything still remains the same. Any other question?
Sir, I had a doubt in the previous slide about predictor.
Yes.
Sir, I think that it will be for the 2 branches that you have taken, it will be 50% and 100%, because each time the first branch predicts something, the second branch will always try to override it to true.
Okay. So let us see this way. See, this is, okay, let us do it in a new slide. Okay, my first branch is resolving like this for whatever data which is coming in. That is branch 1. And branch 2 is always resolving like this. And unfortunately, both of them share the same predictor bit. And that is for the reason of aliasing. That means the last few bits are the same. So now let us say the first one is saying that, let us assume that it is starting from, say, taken. And, if I had taken is not taken, then that wouldn't have make any difference because this is going for infinity or very long time. So let us say the first one is taken. So the prediction for this one is correct. So the prediction bit it would put is taken, which would also be correct for here. So it will say, okay, keep the prediction as taken because last time it was taken. So this time it will be not taken. Now this branch would come and take a look at it. So it will say, okay, the prediction is taken, but it will turn out to be wrong. Why? Because actual thing is not taken. So it will say next time when I come to this branch, I will put it as not taken. So next time when it comes here, because they share the same thing, it would say, okay, actually I don't have to take the branch. So prediction is not taken, but the actual outcome is taken. So you are wrong here. Then, it would change that, last time it was taken. So then, it will come here and it will be correct. And then, you can keep on following. This would be correct. This would be wrong. This would be wrong. And you can keep on following this.
Sir, but in the lab we were told that both the prediction overrides would occur for in the same iteration. So if it is in B1, if it is not taken, then in the next iteration's prediction it will be N. But for B2, since in the previous iteration T was true, therefore in this iteration it had overridden and therefore T is true.
Okay. I am not very sure in what context they had said it, but let us say
Sir,
this,
some
yes.
you make change the question, right? In the lab, there was a different question that both branch has their own prediction.
Okay. Okay. So for this one, which I'm saying of aliasing, this is the correct version. So without going into too much discussion, this is the correct answer for aliasing between two branches B1 and B2. Say B1, when it changes the branch, it would keep it, there's a prediction bit, and both B1 and B2, they are looking at, because their address is same, so they are looking at this predictor. So this is a 1-bit predictor sitting over here. And they would keep on changing this according to their last result. So B1 would change it and B2 will also change it. Thinking, and then, whatever prediction is written here. So B2 will write so in the end, what would happen is that B1 will follow what B2 did last time and B2 will follow what B1 did last time. So that is going to be the problem. And that is only in the case of aliasing, right? So, if there was no aliasing, then, if they had both of them had different ones, then this will always be correct and this will always be wrong. Okay. Okay. Hello, the person who has asked the question, are you satisfied?
Yeah, actually there was aliasing in the lab question as well. So
okay, then assume that this is the correct answer. Okay.
Okay, sir.
Because this question was specifically designed to show this, that B1 will end up doing what B2 did last time, and B2 will end up doing what B1 did last time. Okay, any other question? Okay, so I wish you all the best for exam. It has been a joy teaching you, and I enjoyed teaching you. I hope you also liked something, because this is one of the things that you should carry over for other courses that you study, and probably try to make correlations, whatever you learn in your high performance computing, whatever you learn in your programming, because hardware and software development go hand in hand. And if you maybe in 2 or 3 years, when you go out, the question of hardware versus software will become even more pronounced in industry. That should you write this program in C language and execute using a compiler, or you want to write it using a hardware description language and solve it in FPGA so that execution can be faster. So I absolutely enjoyed teaching you, and I wish you all the best. And if you want any help in future, if you want to do some work in this particular area, then you're always welcome to approach me. Thank you very much, and all the best for. Yes.
Thank you,
Sir, I would
sir.
like to ask, like, how many questions would we have in exam? Because it's not an excuse, but like in all the papers we had in past sems, writing subjective answers has been a bit difficult, considering the time management thing.
Yes. So I mean, I need to design the paper, and I would ask you. I mean, as I told you, the paper would be slightly lengthy. So I mean, I would not wish that the paper is short and people just finish first, and then there is a temptation of checking with each other or sending messages on WhatsApp. So I would keep the paper lengthy, but then the grading is a relative grading. So if it is lengthy for everyone, then you are not in trouble. But then asking a lengthy paper, I have found out that it can separate out smart people, really, really smart people, from average people. Yeah. Okay, so thank you very much, and we'll meet again during exam.